Physicists like to think that all you have to do is say, "These are the conditions, now what happens next?" Richard Feynman. So what had seemed like a dilemma or Murray-Gell-Mann's quark model, namely, why haven't we ever seen a quark if these things are real, is now actually a mathematical consequence of the theory that's developing. So that's nice. It's not a proof that the quarks exist, but it's at least preventing you from throwing away the idea of quarks, because the model itself is consistent with the fact that you will never see a quark by itself. In fact, this idea explains exactly why you either get a quark or anti-quark, which is overall colorless, or three quarks, which is overall colorless. But nothing else. You don't get a quark and a quark because you can't add two primary colors and get white. If you don't have white, you have got incredibly strong forces, and that's going to stack another quark in there to make a baryon. It might even create a quark out of the vacuum if it has to, because you can't just have a colorful object all by itself in the laboratory. So this theory is beginning to explain the details of what Mr. Gell-Mann had just proposed, an almost ad hoc model. That's what you want. You want your theory to explain the feature of the model and make them quantitative. There is another aspect of the quantum chromodynamics that makes it extremely appealing. What I want to head toward now is, why should we believe in a theory that's so hard to calculate with? Why should we believe in the QCD? Why do we believe in the existence of the quarks? We are going to be seeing more and more evidence in future lectures for why we believe in these things as being real. But let me tell you some more reasons right now. What about if you go to the other direction? What if you take two quarks and you try to squeeze them together? You can do that by looking at a proton with a very high energy particles. High energy means short distances, so you are looking with a microscope at smaller and smaller distance scales. If you are looking for two quarks close together, it's again very much like a rubber band. When you stretch a rubber band, there is a lot of energy in that system and it wants to snap back, and the force are not strong. But if you try to squish a rubber band, there is no resistance at all. It's a floppy, and the same thing works out in the theory of quantum chromodynamics, as the quarks get a distance much smaller than about a femtometer, than about 10 to minus 15 powers meter. The force actually get very weak, so inside of the proton, the three quarks are almost free particles. They are just roaming around. If they get a little bit too far away, they get snapped back. But while they are in the proton, they are quite happy and sort of loosely bound. What this means is that over the years, from the early 70s, when this theory is proposed, until today, as you build higher and higher energy machines, and you are looking basically with a finer and finer microscope, what you find is that the particles you are observing, the quarks, are getting less and less strongly bound. They are getting more loose, and the looser bound they are, the easier it is to calculate. This is a kind of a wonderful twist. Usually, as you build higher energy machines, new accelerators, all hell breaks loose. You get a new particles, you don't know what's going on, it gets more complicated. But now we got a theory that goes the other way around. The higher energy, the higher tech your detectors and accelerators get, the better we can do the calculations, the more accurately we can predict what's going to happen. So we can actually make predictions, numerically quantitative predictions about behaviors at high energy much better than we can do at the old. Right. 1960s low energies, right? So this is again not a proof that the quantum chromodynamics is correct, but certainly a nice compelling reason to take it seriously, right? The more high energy the experiment gets, the more accurately we are able to test and verify it. If you think in the language of the Feynman diagrams, the coupling gets weaker, and therefore those complicated diagrams become numerically less important and your calculations get easier and more reliable. Right. Let's talk about the other reasons why people believe in the quarks and QCD. What about this story of confinement? What would happen if you really whacked a quark hard? What are you going to see in the laboratory? You send in the electron beam, and one of the quarks is going to go flying. The other two are kind of stunned and sit behind for a moment because of their inertia, and one of them is running away, stretching that lava band. A stretched lava band, and or in this case a stretching gluonic field, has lots of energy in it. All energy that you gave to the particle is now going into the gluonic field, and in the quantum mechanics, if you've got a lot of energy in a small space, what can happen? You could produce a quark-antiquark pair. You can produce matter and antimatter spontaneously out of that energy, right? It's E equal mc square put together with the quantum mechanics. So, as the rubber band stretches, it might snap back, which could just be leaving you behind with a rattling proton, but it might also essentially snap. The rubber band snaps, and at the point of snapping, you get a particle-antiparticle pair. Let's think in detail how this would work. You left two quarks behind and one quark is running away. You produce a quark-antiquark pair. How are they going to line up? The quark that's produced is going to stay behind, and the antiquark that's produced is going to go along with the quark. So what are you going to have? You are going to have a baryon left behind. You started with a baryon of the three quarks, and you end with a baryon of the three quarks. But now you've also produced a quark-antiquark pair, a pion or something like a pion. Some mesons a heavier version of the pion. And if you have enough energy, the rubber band might snap a bunch of times while that quark is running away, and so you should get a little scream in a straight line of pions running away from the baryons. And that's exactly what was seen in the laboratories. These were called quark jets, and when you smash an electron or particle into baryon, what you see is bubble chamber picture, or more sophisticated version of the bubble chambers nowadays, electric version of the bubble chambers, right? And you can actually see a straight line, a jet of the particle flying off, and you are almost directly seeing a quark, but not quite, because the quark always combine together to form mesons or baryons in the laboratory. But it's extremely close to direct evidence, and in fact you can see multiple jets. As you go to higher and higher energies, you might share that energy between two quarks. We'll see two jets and three jet events, and they all agree quantitatively. You can make predictions from the theory of the quantum chromodynamics, like how many particles in the jet as a function of the energy, which way do they go, how do they recoil, and it all works, it all ties together very nicely, huh? Here is another argument, also a very direct argument, for the existence of quarks. Think about Mr. Rutherford experiment, going way back to the early 1900s. This is a prototype particle physics experiment. You have a beam of particles, you strike a target, and you look and see how they scatter. What do? Do they go through? Do they bounce backwards? You are trying to figure out what's inside your target by looking at how particles bounce off it. Now, this experiment has been repeated a million times and in a million different guesses. For example, Mr. Hofstadter in the 50s did that experiment with electrons hitting proton, and he discovered that they were acting like the proton was kind of the smear of electric charge. That's because the electron's energy was not too high and not too low. It was high enough to see down inside the proton, but not high enough to see down all the way to the size of the quark. So it was just seeing the average of these quarks that were buzzing around, and so it's a smear. But what would happen if you go to higher energy still? The higher your energy, the smaller you are looking. You would think that at high enough energy, you would begin to notice that there really are little nuggets, little hard objects inside the proton. That's our model. That's what Murray-Gell-Mann and ultimately QCD propose, that the world is made of a little real hard object called quarks, and they bind together by the strong force. That's what the proton is. For example, if they are real, you should be able to bounce off of them. So there was a laboratory built in the 1960s called the Stanford Linear Accelerator Center. It's a fabulous physics facility. It's still going strong, and there have been many Nobel Prizes that have come out of what is now called SLAC. It was built in 1966. It's not a cyclotron. People had evolved beyond always building cyclotrons. It's called a linear accelerator because it's accelerating electrons, and if you make an electron go around in a circle, even a big circle, it's going to radiate away some of its energy, and that's what waste flow. But if you make it accelerate in the straight line, it doesn't radiate away so much of its energy. So what Stanford has done is, for 2 miles long, you've got a little particle accelerator, and then another one, and then another one, and another one, all in a straight line. So by the end, you've got this enormously high energy beam of electrons. And in the early 60s, late 60s, early 70s, this beam was aimed at the protons. So it's like a repeat of the Hofstadter experiment, but at higher energies, at a bigger magnification. Now what did they see? Well, they saw every now and again an electron would bounce backwards. So this is like a Rutherford all over again. We are seeing a little nugget inside of the proton. So that's a direct physical evidence that you are walking into something solid instead of just hitting some sort of a smear. Now at first, when people saw this, they said, yeah, could be the quarks. But people didn't quite believe in the quarks yet. So they said, look, let's be as skeptical as we can be. Maybe it's a quarks. Maybe the quarks picture isn't right, and maybe there is something hard and small and charged inside of the proton. But it's not a quark, it's just a part of a proton. Maybe there is not 3 and all of this stuff that we've been deducing. So they were a little bit skeptical at first. Instead of calling them back quarks, they called them partrons for the parts of the proton. I believe it was Mr. Feynman who actually came up with that name. And as the years went by and the experiments refined, you could begin to make quantitative conclusions about, for example, what's the change of the object that you are bouncing off of. The more charge it has, the stronger an electron's going to bounce, and so you can begin to collect the data which tells you that. And in fact, the charges turned out to be 2 stars and -1 star, which is just what the Quarks model says. And you can look at the angular momentum of the process process and deduce what's the spin of those little sparks. And again, the partons, again, the partons, whatever it is you are hitting, and again, it came out to be 1/2, just like the quark model. Patrons, yes, patrons. So, I would say over a period of 5 to 10 years after those original experiments, which were obviously indications that there is something in there, the idea that they might be quarks got stronger and stronger. And now, we have this enormous plethora of the data from a bunch of the facilities, not just Stanford, that indeed all the properties that we attribute to the quarks are being demonstrated. These experiments are called deep inelastic scattering. That's a buzzword in the physics community. Deep, because it's ultra high energy and you're plowing light down into the core of a proton, looking for the quarks. And inelastic is a physicist's technical word for smashing into the Smithsonian's, right? You're taking an electron and you are whacking it into a proton and just blowing that thing apart. And you're looking for not all the spray that comes out, although people are looking at that now, but you are just trying to follow that electron and see what it does. It's like throwing a rock through a plate's glass window, and you are not watching the shard of glass. You are just looking to see what the rock does. You can learn something about glass by seeing how the rock behaves as it goes smashing through. Right. Let me give you a little metaphor that I like to think of when I'm trying to ask myself whether I believe in the physical existence of the quarks. Once upon a time, people knew about the planets in the solar system going from Mercury in the middle all the way out to the Neptune, near the outside edge. People didn't know about Pluto at a certain point in the time, and if you look certainly at the orbit of Neptune, you discover that it doesn't quite obey Newton's law. It doesn't quite go in the perfect ellipse, and you ask yourself, why not? I can think of two explanations. Maybe Newton's laws are wrong, our model of the solar system is wrong, or maybe there is a simpler explanation, maybe there is another planet out there that we haven't seen yet. Pluto. And in fact, we could deduce its position and its mass and its orbit just by looking at the other planets. And to me, this is a situation with quarks. We can't see them directly, we can't even see atoms directly, but we can see their consequences on their systems very differently, quantitatively, and there is no doubt in any physicist's mind, at this point, at least, many physicists' minds, that quarks are as real as Pluto. Thank you.